Good morning, students. I welcome you all for another lecture on the course Microprocessors and Microcontrollers. From last few classes, we are discussing about 8051 microcontroller instruction set. In that, we covered different groups of instructions like data transfer instructions, arithmetic instructions, logical instructions, bit manipulation instructions. In this class, I am going to discuss about another group of instructions in 8051 instruction set, that was branching instructions. Right, my first point about this branching instructions is, basically these instructions are used to change the program execution sequence from one location to other location, either unconditionally or conditionally. I repeat my first point. This group of instructions are used to change the program execution sequence from one location to other location, either conditionally or unconditionally. So see here friends, for example, I was executing this program. This program is start from a location address 1000H. After execution of this particular instruction, I would like to execute the instruction which is there at some 2000H. Then what I have to do is, definitely here that instruction is branching, and that branching instruction destination address is at 2000, then only my execution was shifting from this instruction to this instruction. So here the instruction must be branching instruction. So the main job of these branching instructions is, these are used to change the program execution sequence or program execution flow from one location to other location, either unconditionally or conditionally. So for that purpose, I took the help of this branching instructions. That is the first point. Coming to number 2, this group of instructions have a different names. This group of instructions we can also call jump instructions, or transfer of control instructions, or program flow control instructions. So there are 3 more alternate names for branching instructions. Those are jump instructions, or transfer of control instructions, or program flow control instructions. And basically these branching instructions or jump instructions are divided into 2 different groups. So those are, one is unconditional branching instructions, and number 2 is conditional branching instructions. I repeat, these branching instructions we divided into 2 groups. Mainly those are unconditional branching instructions, that was the first group, and the second group is conditional branching instructions. Now we will go and discuss these are groups one after other with what are the instructions that are present in that particular group. First I start with unconditional branching instructions. So unconditional branching instructions, the name itself indicates, without considering any condition, the program execution sequence changes from one location to other location. So see here guys, that point I written, these instructions are used to change the program execution sequence from one location to other location without considering any condition. Just like that only, I change my execution sequence from one location to other location. So these are unconditional branching instructions. Coming to your 8051 microcontroller, we have a good number of unconditional branching instructions. See here friends, in this table we have those unconditional branching instructions. In that, first one is JMP, means jump unconditionally. One important thing regarding this JMP instruction is, always you have to go and use indexed addressing mode only for utilization of this JMP instruction. See here friends, the example is JMP space at the rate of A plus DPTR. That means here I have to go and calculate the destination address by adding of DPTR value with accumulator value. So whatever the result I was getting, that is becoming as a destination address. So for example, you consider this is a program this program is start from some memory location address 1000H. Somewhere else here I write that instruction JMP space @ of A plus DPTR. So once my controller execute this, what happens is definitely it will change the program execution sequence from this point to some other point. What is some other point address? That address was provided by the combination of DPTR and accumulator register. For example, DPTR value is some 2000H and accumulator register A value is some 50H. Then first I do addition between these two. My result is 2050H. This is now my destination address for this jump instruction. So one thing you remember friends about JMP, first thing it is unconditional jump, and number two is we always use indexed addressing mode for representation of this JMP instruction. Yes. Coming to the next one is nothing but A call. A call means absolute call. A call means absolute call. One thing you remember friends, basically the call instruction, this call instruction is used to call a subprogram into main program. Originally here what happens is, our program execution sequence was changing from main program to subprogram. We know that when we are go for subprograms, whenever if you want to do a particular operation some n number of times in n number of places of my program, then what I have to do is that particular operation related instructions I write separately from main program. Due to this, what an advantage I was getting is, instead of writing those instructions n number of times in my main program, the main program size was increases. Once the main program size was increases, it automatically influences the occupied space in the memory. In order to reduce the memory requirement, then what I have to do is I can go and write the instructions which are needed to the particular operation separately from main program. That separately written instructions I can call as subprogram. Whenever I want it, I just call that with the help of an instruction is called call. Call instruction is used to call a subprogram into main program. But originally here what happens is, our program execution sequence changing from main program to subprogram. For better understanding, see here friends, this is your main program. Let you can assume this is your main program. I simply written as MP, means main program, and this is a subprogram. I written as SP. Let you can assume main program is at some 1000H and subprogram is start from a location address 2000H. I want this subprogram in my main program here, and second time here, and third time here. Then what happens is, if I write this here, what happens is the total size of main program is increases. Once the main program size is increases, automatically it occupies more memory. So in order to overcome that, what we have to do is we write our subprogram separately from main program. So then here I want a subprogram. Here I can go and use a call instruction. By execution of that call, our execution is shifted to subprogram. Generally what I am saying, call instruction is used to call a subprogram into main program. But coming to reality, what happens is our execution flow changing from main program to subprogram. After finishing of this subprogram execution, again I come back to the main program. Again it will go and execute this instruction, and at this time again I want this subprogram. Then by using call instruction I change execution sequence to subprogram from main program. After execution of this, again it will come back, and here again I need subprogram execution. Again by using call instruction I shift execution to subprogram. After finishing that, again I come to main program, and it will continue the execution of the rest of the instructions. So basically the call instruction is used to call a subprogram into main program. But originally here what happens is our execution sequence changing from main program to subprogram. You remember that. Now coming to A call. A call means absolute call. A call means absolute call, And if you go for an example, A call space 11-bit address. That means here the difference between our main program and subprogram, the number of locations between this main program and subprogram must be within 2K, because 11-bit, that is nothing but the number of combinations we are getting is 2K combinations. When I was using a call in case of 8051 microcontroller programming was the main program and subprograms must be exist within 2K, then and only I can go and use an instruction is a call to call a subprogram into main program. I repeat once again, friends, you remember when I was used a call is whenever my main program and subprogram both are exist within 2 kilobytes of memory space, then to call a subprogram into main program, I have to go and use an instruction is a call. So a call means absolute call. And coming to one more variant of this is L call. L call means long call. L call means long call. If you go for an example, L call space 16-bit address. That means whenever the subprogram and main program may exist in entire 64 kilobytes of memory, then I can go and use an instruction is L call to call a subprogram into main program. I repeat, so your 8051 maximum it can able to address a memory of 64 kilobytes because it has a 16 address lines. Once your subprogram present in any location of your main memory, then I can go and use an instruction is L call to call that subprogram into main program. So that you have to remember. And one more important thing is wherever you found absolute or long. So here whatever the address here you return, that is absolutely unsigned number. If it is an unsigned number, then automatically that number is positive number. Once it is a positive number, then automatically your destination, that means your subprogram must be present after completion of main program related memory locations. So here the condition is satisfied. My main program finishes before this 2K. I can call this a 2K subprogram with the help of this a call instruction, because the distance between this main program and subprogram is not more than 2K. If it is more than 2K, then I have to go and use one more variant, that was L call. L call means long call. So finally what I conclude is this A call and L call, both the instructions are used to call a subprogram into main program. So that is about this. And one more instruction we are used when we are communicating with the subprograms, that was RET. RET means return from subprogram. Return from subprogram, and the speciality of this instruction is this instruction comes under implied addressing mode. That means we are not writing any operand beside of our RET instructions right away. You remember, friends, so this RET instruction basically used as a last instruction for any subprogram, or I can say in another way, this RET instruction is used as terminating instruction for any subprogram. By execution of this RET instruction, our execution sequence changing from subprogram to previous stopped program. So that is an important thing regarding to RET. And coming to one more variant is RETI, means return from interrupt service routine. We know that your controller supports different interrupts, and your controller is accepting any interrupt from a device, and it will provide a servicing for it. In that process, your controller can go and execute a program that is called interrupt service routine. Once it's successfully execution of that interrupt service routine, again it will come back in execution to the previous stopped program. In that case, to return to your previous stopped program, that interrupt service routine must have a return instruction. That return instruction here is RETI. That means I can say that this RETI, which is nothing but return from interrupt service routine, this instruction is used as terminating instruction for every interrupt service routine ISR. So that is about this. And next coming to another jump related instructions, One is SGM, that means short jump. Next is AGM, means absolute jump, and LGM means long jump. I'm already told you just now, wherever you are getting absolute or long, definitely the destination address is after source address. That you have to do. That means, or I can say in another way. So whenever you are getting absolute or a long, your jump must be forward. That means you are always goes to the next locations. We never goes to the previous locations. That you have to remember. Coming to first A jump means absolute jump. So I can jump to the destination whose address is in between my 2K, because A jump is 11-bit address. That means your source and your destination, these two must be within 2K. Then I can go and use an instruction is A jump. Once the distance between our source and destination crosses 2K, then I have to go and use an instruction is L jump, means long jump. Then what is this S jump? S jump means short jump. See here friends, an example. S jump space 8-bit relative address. That means this here 8-bit is a signed number. Once it is a signed number, you have a negative numbers as well as a positive number. So here your relative address is an 8-bit. Once it is an 8-bit, then maximum positive value we are getting is 127 and the maximum negative we are getting is 120. That means once you have a negative number, that indicates we are not only moving to the next locations, we can also move to previous locations. So only with the help of SGM, we can move to either previous locations or to next locations. But by using absolute jump or by using long jump, we never go to the previous locations. We always goes to the next locations. That you have to remember friends. So all these instructions we consider as unconditional branching instruction. In this case, we are not using any condition to change our program execution sequence from one location to other location. That's why here these 8 instructions we consider as unconditional branching instructions of 8051 microcontroller. And next, I was shifted to the second group of branching instructions. Those we can call as conditional branching instructions. The name itself indicates this group of instructions are used to change the program execution sequence from one location to other location by considering some condition. By considering specific condition only, we change the program execution sequence from one location to other location. That means once the specified condition in the instruction was satisfied, then and only our execution sequence changes. If the specified condition in the instruction was not satisfied, then your controller simply ignore that branching instruction. It will go and execute the next instruction which is there after that branching instruction. So from this it is very clear friends that those an unconditional branching instructions are compulsory jump instructions. That means once we have written any unconditional branching instruction in our program, once your controller can execute it, no, the program execution sequence changes. But coming to conditional branching instructions, it may changes or it may not changes. It changes only when the specified condition in the instruction was satisfied. Otherwise, the execution flow will not be changes. That's why these conditional branching instructions are not compulsory jump instructions. That you have to remember friends. Next, coming to different instructions, what we found in this particular group. And one more important thing is all these conditional branching instructions are relative jumps. What is the meaning of this? By using a relative jump, you can move to previous locations or you can move to the next locations. That means you go for forward or you can go for backward. So that facility is available for relative address. So whatever the conditional branching instructions we have in this 8051 microcontroller, all are relative jumps only. So that you have to remember. And coming to the instructions what we have, the first one is JC. JC means jump if carry is set. Jump if the carry is set. Carry is one of the flag which was present in our program status code PSW. Once that carry flag is set to 1, then and only whatever the address we have written in the instruction operand field, that is considered as destination. Otherwise, your controller simply ignore that instruction, it will go and execute the next instruction. For example, for better understand, I take a small example. So let you can assume friends, this is my program. Somewhere else here I written an instruction JC some 70H. JC space 70H, because always you have to go and use 8-bit relative address. That's why here I can consider only 2-digit hex number. 2-digit hex number is nothing but 8-bit address. So JC space 70H. That means jump to 70H only when the carry flag in a PSW is set to 1. If it is not set, your controller simply ignore this and it will go and execute the next instruction. If this condition is satisfied, then our execution sequence is changing from this to this concerned destination address. So that's the meaning of this. Opposite to this, the next one is JNC. Jump if carry not set. Previous JC means jump if carry is set, but now jump if carry is not set. So again condition is same. So instead of JC, here you write JNC. Jump if the carry is not set. If the carry flag is not set, that means that by execution of previous instruction, your carry flag was not set. Then if I go for this instruction execution, if the carry is not set, then I didn't go to this. So I go to this. The carry flag is not set, then I go to this. If the carry flag is not set, then I simply ignore this and I can go for next. So it is exact opposite to previous one. Previous one case is, in order to change execution sequence flow from this location to this, the carry flag value must be set to 1. So coming to the next case, the carry flag value must be 0. That's it. And coming to the next one is JB. JB means jump if specified bit is set. Jump if a specified bit is set. See here guys, so what the bit is, you have to write that bit in the instruction operand field. So whatever the bit address here we written, that bit is set to 1, then only we can go to this relative address. If the specified bit is not set, then simply your controller ignore this instruction and it will go for next. So it is similar to JC, but in JC case we are verifying carry flag condition, but coming to JB case, whatever the bit we are written in the instruction operand field, we are going to check it. If that is checked, then I can go on consider that 8-bit relative address, which is my destination address. Otherwise, I simply ignore that entire instruction. Similarly, my next instruction is J and B. That means jump if specified bit is not set. Specified bit is not set. What happens in case of previous one JB? Jump to relative address only when the specified bit is set. But now we jump to relative address only when if the specified bit was not set. That means if a specified bit was clear. So see here guys, J and B space B comma 8-bit relative address. I consider this 8-bit relative address as a destination only when here the specified bit was not set, or here the specified bit value equal to 0. So it is similar to JNC. In JNC case, I was checking carry flag. If it was clear, then I can go to relative address. Coming to JNB, if the specified bit was clear, then I go to relative address. So that is the basic difference. And next coming to JZ. So JZ, that means jump if accumulator is equal to 0. Jump if accumulator is equal to 0. That means in previous 4 instructions, we designed those branching instructions based on bits. Carry flag is a bit, as well as a specified bit also a bit itself. But now coming to JZ and JNZ, these 2 instructions are purely designed based on the content of accumulator register A. Coming to the first case, JZ, that means jump if accumulator is equal to 0. That means jump to this relative address only when the accumulator register A value equal to 0. Because in case of 8051, you have 2 accumulators. One is A, which is called as a primary accumulator, and second one is register B. It is also we can consider as an accumulator, but that was a secondary accumulator. So here this accumulator here is that we are talking about register A. Register A. Jump if A is equal to 0. A means accumulator is equal to 0. Otherwise, you simply ignore that instruction. You continue the execution of the rest of the instructions. And opposite to this, that was J and Z. That means jump if accumulator is not set, or jump if accumulator is clear. So once your accumulator is loaded with a 00H, or accumulator value have a 00H, then you consider that a bit relative address. Otherwise, you simply ignore it. And coming to the next one is JBC. It is again a very important one. That is JBC means jump if a specified bit is set, and before jump to that, first you have to clear that bit itself. So see here friends, JBC space B comma a bit relative address. It is similar to this. It is similar to JB instruction. But in addition to that, here we are doing one more thing. That was before jump to relative address, first you have to go and clear what are the bits we consider for jumping. That's important. But in case of JB, we are not doing that. Once the specified bit is set, we simply jump to the destination address. That is as it is in case of JB. The same thing was followed in JBC, but in addition to that, here what happens is, before considering a relative address to reach a destination, here we have to clear the specified bit. So that's why JBC instruction is extension for JB. So that you have to remember. And next we have two more instructions. These two are very important for us. One is the DJ and Z. DJ and Z. Here D represents decrement. Decrement. Decrement the specified register what we have placed in the instruction operand field. First you have to decrement it, its content by 1. After that you have to go and verify that register content is equal to 0 or not. So here the rest of the instruction is J and Z. J and Z means jump if not equal to 0. First you decrement the specified register value by 1. If that register value is not equal to 0, then go to specified 8-bit relative address. If it is equal to 0, you simply ignore this, you come out of it. It will go and execute the next instruction. So this instruction is a combination of two. One is an arithmetic instruction, that is decrement, and the one is a branching instruction, that was J and Z. So you remember friends, this D, J and Z is a combination of two instructions. One is the arithmetic instruction, which was a decrement, and second one is a conditional branching instruction, that was J and Z. Finally, the meaning of D, J and Z means first decrement the specified register content by 1 in the instruction operand field. Thereafter, that register value is not equal to 0, then go to specified relative address. That's the meaning of this. And coming to the last, CJ and E. Here this C represents compare, J and E, jump if not equal. So you remember friends, this is only the instruction in entire 8051 microcontroller. This instruction have 3 operand fields. See here friends, this is the one operand, this is the second operand, and this is the third operand. In entire 8051 instruction set, this is only the instruction which may have 3 operand fields. And again it is a combination of 2 instructions. One is a compare. Compare is arithmetic related instruction. Arithmetic related instruction. And J and E, it is again conditional branching related instruction. Previous case also it is arithmetic instruction decrement and conditional jump instruction J and Z. Similarly, here also first what we do is we compare accumulator value with this immediate value 30H. If these two are not equal, then consider this relative address to reach destination. Otherwise, you simply ignore that instruction CJNE space A comma hash 30H comma 8-bit relative address. So this is about our branching instructions. I hope you understand the branching instructions of 8051 microcontroller. So with this, we finishes the instruction set of 8051 microcontroller. Thank you for patient listening. We will meet in next class. Thank you once again.